Welcome to Beyond the Comfort Zone. Today, you're joining us for something special. We're diving into the architectural insights with KING-KAMBUF PS Architecture Daily Mentorship Digest.
And this isn't your standard review.
No, not at all. We're really stripping away the conventional wisdom today, looking past the fundamentals. We're aiming to move directly into the strategic, almost PhD level material that really defines what mastery in architecture and engineering looks like now.
That's the goal. Our mission for you today is a kind of rapid synthesis of some very high-level intelligence. We're not, reviewing building codes. We're trying to review the future of building.
And the material we're looking at, it really suggests a huge shift is underway.
A fundamental one, yeah. The core idea is that architecture isn't just about static form and, aesthetics anymore. That's table stakes. It's becoming this strategic, responsive, and policy-integrated discipline.
Policy integrated, I like that. So it's designed to manage all these invisible forces that really dictate how a project performs in the long run?
Exactly. Forces like, say, atmospheric chemistry or deep earth geology, even political governance. These are now design parameters.
So if you're out there and you want to be truly well-informed, to be that master builder who really gets the entire system, you have to understand how heat and politics and the geological movement of the Earth are now just as important as a steel beam.
Absolutely. We're seeing a move away from the idea of a fixed structure to a responsive system.
Yeah.
A successful building today has to anticipate and integrate solutions for everything. Global warming, seismic shifts, political disruption, utility failures, and it has to do it all at the same time.
And we have some, I have to say, genuinely compelling content to unpack today from the digest. We're going to dissect exactly how foundation engineers are using cryogenics to stabilize frozen ground up in the Nordic regions.
And from there, we'll look at structural steel being developed in Japan that literally changes its molecular properties based on the cryo levels in the air around it.
Which is just mind-bending. And then maybe the most surprising life safety lesson I've seen in a while, why the compact, high-density shelving you see in a library has actually become one of the most significant multi-story lateral hazards that we now have to engineer against.
It's a fascinating and kind of terrifying collection of challenges.
It is. Okay, let's unpack this high-stakes material.
So we should probably start with that first big theme, the interface between engineering and these huge planet-scale dynamics.
Engineering the extremes.
Exactly.
Yeah.
The global intelligence flowing through the AEC community, the architecture and engineering world, it all shows that structures have to become inherently responsive. They can't be passive anymore. They have to react to environmental threats, geologic conditions, and often at the extremes of temperature and volatility.
So let's start at one of those extremes, extreme cold. Specifically, this challenge with degrading permafrost. We're talking about places like Finland, Alaska, Mongolia.
Right. And in these transition zones, conventional foundations are failing, just completely failing.
So the industry's response is something called a cryogenic stabilized deep foundation. What's driving this?
Well, in a word, it's climate change. It's a direct and, frankly, a pretty desperate response.
Right.
You have this permafrost, this ground that's been frozen solid for millennia.
Which is historically great to build on, right? It's like bedrock.
It's like building on concrete. It's incredibly stable. But now it's thawing. And as it thaws, you get water, you get instability, and the soil loses all its bearing capacity.
Which leads to what the digest calls massive differential settlement.
That's the killer. It's not that the whole building sinks evenly. Parts of it sink while other parts stay put. And that uneven movement, that differential settlement, just tears a structure apart from the foundation up.
The traditional solution, I assume, would be just to drill deeper piles, but that doesn't work here.
It doesn't, because the instability is thermal. It's not just a load-bearing problem. So the cryo-stabilized solution is, it's completely different.
So what is it? What are they actually doing?
They deploy these specialized pile systems that have temperature-regulated sleeves, or things called thermosiphons. Instead of just trying to mechanically resist the unstable ground, you actively manage the thermal profile of the soil itself.
You're managing the temperature of the ground around the foundation?
Precisely. The piles are designed to wick heat away from the foundation area. Or, in the more active systems, they actually use a refrigerant loop, like in your air conditioner, to maintain a stable freezing temperature in the surrounding soil all year round.
Wow. So that's the crucial insight here then. Foundation engineering is no longer just geotechnical. It's become thermal geotechnical management.
That's the phrase. You're not just calculating compressive strength and soil friction anymore. You're calculating BTUs and thermal transfer rates over a 50-year life cycle.
It sounds incredibly complex.
It is. And the challenge for the master builder who's sketching out this strategy is really twofold. First, maintaining that thermal consistency requires reliable power, reliable monitoring systems, and these are often in really remote regions where that's a huge ask.
And the second challenge,
The second is you have to actively mitigate something called frost heave.
which is the opposite problem, right? Where excess moisture freezes and expands, and it pushes the structure up.
It's this dual-sided thermal battle. You need the stability of the frozen ground deep down, but you have to avoid the destructive expansion of these segregated ice lenses that can form near the surface. It's a very delicate balance.
So you're freezing the deep ground while trying not to freeze the shallow ground too much.
Exactly. It requires meticulous detailing of that pile-sleeve interface. And sometimes you have to use sacrificial layers of, say, granular fill to sort of buffer the seasonal freeze-thaw cycles right near the surface. You're trying to ensure the cryo system only locks in the deep, stable permafrost.
Okay, let's flip that thermal switch completely. From extreme cold to extreme heat. The digest talks about magma thermal district systems. This is happening in Iceland and Indonesia.
Right, we're talking about urban energy infrastructure interfacing directly with volcanic heat sources.
This is where civil engineering basically becomes geological extraction.
That's a great way to put it. These regions are piloting these massive thermal loops that tap into fringe geothermal gradients, often near dormant or even active volcanic chambers,
So we're talking about heating an entire city district not from a boiler plant.
but from the planet's core. Yes.
The implication for urban energy is it's profound. You're forced to think of the city not as a mechanical consumer of energy, but as a system that's integrated into the Earth's own thermal geology.
It is. And the engineering complexity this introduces is, well, it can be lethal.
How so?
The complexity lies in the integration. That deep magma gradient heat is immensely powerful. It's not just hot water. Sometimes it's superheated steam. It's carrying volatile minerals.
So you can't just pipe that directly into a building's radiant heating system.
Not unless you want to create a bomb.
Yeah.
You have to use these highly specialized multi-stage heat exchangers. They often use non-corrosive fluids like heavy brines in that primary loop to step the temperature down gracefully from, say, 350 degrees Celsius to a manageable 60 degrees for the building systems.
That sounds like a catastrophic failure just waiting to happen if that pressure or the thermal gradient isn't managed perfectly. Thermal overstress is the core danger, I'm guessing.
It is. A single breach in that primary loop or a failure in the heat exchange sequencing could introduce extreme pressure or scalding temperatures directly into public infrastructure. It would lead to rapid system degradation and obviously massive safety hazards.
So the engineering has to be flawless.
It demands fail-safe isolation, redundant cooling loops. You have to manage that incredible energy intensity constantly. It's a huge responsibility.
Okay, from deep in the earth, let's go up into the air. This might be the most forward-thinking concept in the whole digest. Carbon-adaptive structural steel, developed in Japan.
This is truly revolutionary. We're not talking about a coating or a treatment. Metallurgical institutes there are testing steel alloys designed so their actual crystalline structures respond directly to the concentration of atmospheric KIOs.
I have to stop you there. A structure with a built-in environmental sensor that changes its own material performance.
That's what it is.
So wait, if the air quality improves, the building structure literally changes its behavior.
That's the observed effect, yes.
That immediately raises a crucial question for me. If the steel depends on pollution for its enhanced performance, does that create a kind of perverse incentive? Does this material subtly push designers to build in places where pollution is higher to maximize the steel's intended ductility?
That is the essential ethical and strategic question surrounding all adaptive materials. Fantastic point. The observed behavioral change is what's so fascinating. In these polluted urban microclimates where FeO is higher, the steel actually enhances its ductility.
It becomes more flexible.
More flexible, less brittle. It adapts to the environmental stress by increasing its own tolerance for deformation.
So in a heavy urban center with high emissions, the structure is optimally flexible to handle dynamic loads like wind, maybe even minor seismic events. But if we meet our clean air targets, the steel stiffens up and potentially loses some of that dynamic resilience.
Precisely. And this demands a radical shift in how we do structural modeling. You have to integrate these long-term atmospheric shifts into the performance model. You can no longer treat pollution as just a health hazard,
You have to treat it as a dynamic load condition.
as a dynamic load condition that influences the fundamental physical properties of your structural materials over the entire life cycle of the building.
So this means the structural engineer has to start collaborating with who? The climate scientist, the urban planner, to model not just the current pollution level, but the projected change in pollution over, say, 75 years.
Yes, and then select the alloy that provides the most stable performance profile across that entire projected shift.
You're building for a system that is inherently uncertain.
Deeply uncertain,
Yeah.
because its behavior depends on human policy decisions, like future emissions regulations, just as much as it depends on seismic codes. You're modeling structural performance based on societal variables. It's a whole new world.
Shifting from geology and chemistry, let's pivot to governance. This was another huge takeaway for me from the KING-KAMBUF material. The idea that physical infrastructure is now being merged directly with public administration.
It's a fascinating trend.
We are literally embedding regulatory trigger points into the design of pipes and concrete.
And this shift is really driven by a harsh reality. Physical resilience during a crisis, a flood, a wildfire, civil unrest. It's often defeated by bureaucratic inertia or, fragmented political control.
The physical systems work, but the people can't agree on how to use them.
Exactly. So the idea is if the infrastructure is smart enough to handle policy overrides itself, we can ensure continuity of service when it matters most.
So let's scrutinize this idea of governance-integrated utility tunnels. The digest mentions designs in Denmark and Morocco. These are clearly far more than just subterranean spaces for fiber optics and water mains.
Oh, much more. They function as zones of what you might call engineered policy. The design includes specific redundancies, isolation points, where utilities can be rerouted or disconnected or prioritized based on predefined regulatory override protocols.
Okay, so the design team actually has to define these policy to infrastructure triggers. So an example would be the mayor declares a state of emergency.
And the tunnel system automatically diverts potable water from the industrial park to the emergency hospital zone.
Without needing a crew of people to go turn valves.
Exactly. You need a detailed decision matrix that links a legal declaration to a mechanical action. For instance, Policy Trigger A, declared by the Ministry of Public Safety, might legally permit the automatic closure of specific access hatches to the tunnel to prevent unauthorized access during a terror threat.
And at the same time,
And simultaneously, it could initiate the diversion of the high-voltage power lines to a shielded backup conduit 300 meters away. All automated, all based on that legal trigger.
the deep insight here seems to be that infrastructure is becoming the physical manifestation of public administration law. It's where the rubber of policy meets the road of reality.
It is. And the challenge for the designer is ensuring that the physical system is robust enough to handle the potential political volatility. How do you design an interface that responds reliably to a legal decree but can't be, manipulated?
That's the key. How do you prevent it from being hacked, either physically or politically?
It requires building in redundancy for the governance layer itself. You need multiple command inputs, physical key locks, digital cryptographic sign-offs, maybe even old-school mechanical levers that all have to adhere to this legal declaration chain of custody. The infrastructure itself has to be impartial.
It only follows the legally defined threshold, whether that's a flood gauge reading or a signed presidential order.
Precisely.
Okay. Moving to an even more complex intersection of policy and space. Policy-integrated evacuation corridors. This is within mega-informal settlements, with examples from Kenya and Brazil. These are environments where physical boundaries are fluid and legality is often contested.
This is spatial governance negotiated at the most granular human level. It's not like planning a new suburb. You're dealing with millions of residents living in these dense, organically grown structures. You can't just go in with a bulldozer and mandate demolition to clear a path.
So the job of the architects and planners is to map and somehow secure legally protected evacuation corridors, often just a few meters wide, inside these incredibly dense settlements. How do they secure permanence when the physical construction around it is continuous and informal?
Well, they don't use concrete walls. That's the key. They use socio-legal anchors.
Socio-legal anchors. What does that mean?
It means the permanence of the corridor is secured through these complex, community-negotiated agreements, municipal easements, and a whole system of continuous micro-incentives. The physical infrastructure, the corridor itself, is maintained not by police enforcement, but by collective benefit.
Let's dig into the mechanics of that incentive system. What does a micro incentive look like in this context, and how does it actually function as a design element?
It often functions as a kind of conditional property relief. For example, the structures immediately adjacent to the corridor, the ones that maintain the agreed-upon boundary and don't encroach, they might receive conditional access to formalized municipal services.
Like running water or consistent trash collection.
Exactly. Or maybe a property tax reduction on the adjacent land. Something tangible that benefits them directly for respecting that common space.
And the moment they encroach upon that corridor, they lose the incentive.
That's the mechanism. The governance mechanism is the design mechanism. The architect's role here shifts from, drafting a construction specification to drafting a legally binding, community-enforced covenant that ensures the corridor stays open. The policy document becomes the most critical spatial plan of the whole project.
That transition leads perfectly into the next point from the digest, the role of legality in project feasibility, specifically dealing with resource rights, which is a lesson heavily emphasized in the ARE prep material.
This is a really harsh reality check for a lot of designers. The digest makes it clear. Any regional water supply or resource project, a dam, a pipeline, a major aquifer draw, it has to rigorously document the groundwater rights chain of custody from day one, before any design work happens.
So why does that legal step have to precede the engineering?
Because competing legal jurisdictions create conflicts that are guaranteed to delay a project. And often, they stop construction entirely, regardless of how brilliant the engineering is.
You're talking about states fighting over river water.
Or agricultural districts versus municipal consumption, or indigenous land rights. These are legal minefields.
So if a regional water project is engineered perfectly, but it lacks the legally defensible right to actually draw the water, the project is functionally impossible.
It's a paper exercise. The core lesson is this. Public administration, specifically the legality surrounding fundamental resources like water, is a non-negotiable design material. It's as real as concrete or steel.
If you don't design for legal feasibility, your engineering designs are purely theoretical.
Exactly. The legal documents define the project's feasibility just as much as the soil reports do.
Okay, now that we've established that macro context, the political, the geological, let's zoom right in on the physics of the building itself. We're moving into the realm of advanced structural analysis, complex failure modes. This is all about the invisible forces that truly separate mastery from simple compliance.
Right. And this section of the digest argues that true mastery isn't just about preventing a catastrophic collapse, which is the baseline. It's about mastering the forces the structure creates in its interaction with the environment. Forces like capillary transport, wind vortices, and internal thermal stress.
Let's start with the building envelope and a seeming subtlety. Capillary break verification. This is for slab-on-grade construction, especially in semi-arid or seasonally wet climates. Why is this capillary break so essential?
Because capillary action is an invisible but incredibly powerful and continuous transport mechanism. Soil moisture is dynamic. It rises and falls. And capillary forces will literally wick that moisture vertically through the tiny pores, the microchannels in the concrete slab and the underlying soil.
It's like the concrete is a straw.
A very slow, very wide straw. And it carries water vapor directly from the ground into the building's conditioned space.
And that leads to all sorts of insidious moisture issues inside the building envelope. Mold, flooring failure, extra strain on the HVAC system.
And crucially, the digest makes a very important distinction here. This is not the same thing as waterproofing.
How so?
Waterproofing addresses liquid water intrusion, under hydrostatic pressure from a high water table or from heavy rainfall. A capillary break, which is usually a layer of coarse aggregate or a specialized membrane below the slab, is there to prevent the upward suction of moisture vapor.
So you can have a perfectly waterproof basement that still fails because of capillary action.
And it happens all the time. They're distinct, non-redundant layers of performance. If you ignore the capillary break, you've basically designed a humidity problem into the foundation from day one.
Okay. Next up, let's talk about wind, but not just wind speed. The digest focuses on microaerodynamics, specifically wind corner suction on buildings with stepped roof transitions. Why are the standard code multipliers not enough here?
Because standard code multipliers for wind uplift, they assume a relatively uniform airflow over a predictable, simple roof geometry. But the moment you introduce a stepped roof transition, a sudden change in height or slope, the airflow separates. It becomes turbulent.
And it creates what the digest calls secondary vortices at those internal corners.
Yes. The geometry itself creates a self-inflicted hazard. It funnels and amplifies the wind force in Very specific locations.
So it's not the overall wind speed, it's these little tornadoes you've created at the corners of your own building.
Precisely. And these secondary vortices can dramatically amplify uplift forces, sometimes reaching magnitudes 2 or 3 times higher than the surrounding roof pressure. It's a highly localized phenomena.
So what's the solution? How do you even calculate for that?
You have to use computational fluid dynamics, CFD modeling, to map these microaerodynamic hotspots. The core lesson here is that for complex geometries, microaerodynamics dominates over basic generalized wind speed calculations. You have to design your fastener and membrane density based on those localized computational results, not just a generic code chart.
Okay, final point within the envelope. Interstitial smoke purge modeling. This is for double-walled auditorium facades. This sounds like an architectural trend that accidentally creates a huge life safety flaw.
It is a critical lesson in unintended consequences. These double-skin facades, which are great for thermal buffering or aesthetics, they create a large air cavity, the interstitial space between the inner and outer walls.
And if a fire starts in the auditorium,
Smoke can leak into this cavity.
and once it's in that cavity, it basically acts like an accidental chimney.
A huge building-high chimney. Exactly.
Mm-hmm.
Due to thermal buoyancy and the stack effect, that smoke bypasses your carefully designed, fire-rated walls and doors. It migrates vertically, and it can contaminate upper floors or adjacent, supposedly separate fire zones.
That's terrifying.
It is. And the deep lesson is that the airflow within that double envelope has to be intentionally scripted. It can't be an accident. You need active smoke purge systems, dampers, compartmentalization. You have to model that cavity as a pressurized life safety zone, not just a thermal buffer.
Let's shift our focus now to pure structure, starting with concrete. The digest notes the necessity of temperature differential stress checks in thick concrete, specifically in shear walls thicker than about 14 inches. Why is the thickness the critical factor here?
It's purely about exothermic chemistry. When cement hydrates, when it cures, it generates a significant amount of heat. In a standard 8-inch wall, that heat dissipates relatively quickly to the environment.
But in a massive wall, say a 24-inch thick shear wall,
In a massive wall, the core of the concrete remains hot for days, even weeks, while the exterior surface cools down much more rapidly. And that creates this enormous steep temperature gradient between the inside and the outside of the wall.
and that differential temperature gradient leads to restrained cracking.
Yeah.
The hot interior wants to expand, the cool exterior is already solid and restrained, and the result is massive internal tension.
That tension causes microfractures throughout the concrete. The digest terms this silent structural drift.
Silent drift. I like that. It's silent because the wall doesn't necessarily fail outright, but those microcracks are compromising its integrity over the long term.
They're compromising the structural stiffness and the elastic behavior.
So what are the actual measurable implications of this silent drift?
Well, it permanently reshapes the wall's modulus of elasticity. A structure that was engineered to perform in a linear, predictable way under a lateral load might experience increased sway or have a reduced performance capacity decades later, all because its stiffness was subtly compromised during the initial curing phase, years before.
So what's the fix? How do you prevent that?
It means the structural design has to include temperature control protocols during construction. Things like embedding cooling tubes within the concrete pour, or using staggered pour sequencing to allow heat to dissipate. You have to treat the heat of hydration as a primary dynamic load condition, not just a construction byproduct.
Moving from the walls to what's inside the building, let's talk about lateral load anchoring for modular furniture. This is for civic buildings. It seems like a minor maintenance detail, but the digest flags it as a critical life safety requirement.
This is a classic example of where structural engineering meets human factors engineering. In these large assembly spaces, think legislative chambers, multipurpose convention floors, they often use these heavy modular platforms or systems for flexibility.
Right, so they can reconfigure the room.
But if these heavy systems aren't anchored for lateral load, they become projectiles during a seismic event, or even just high wind sway in a tall building.
And the hazard isn't just that the furniture might break, it's that its movement disrupts the escape route.
That's the real danger. These loose modular platforms shift under lateral movement, and they fundamentally alter the occupant egress patterns. They create unexpected obstacles, pinch points, bottlenecks, right when a rapid clear exit is mandatory.
So the lesson is that you have to view the occupant's behavior plus the furniture layout as a single composite egress system.
And it has to be engineered together. The furniture must be engineered to remain in place to guarantee that the designed exit pathway actually remains open in an emergency.
Okay, now let's cover that really surprising point we teased at the start. High-density, compact shelving, the kind you find in large libraries or archives, being classified as a multi-story impact hazard.
This is a really non-obvious piece of structural engineering. These compact shelving systems, the heavy, rolling stacked units, they can reach immense heights and contain an incredible amount of mass. Paper is heavy.
Structurally, they behave like stacked, rigid masses, maybe 10 or 15 feet tall.
Right. And under lateral movement, say a moderate earthquake, the inertia of that mass is just enormous.
The problem, I'm guessing, is how they're anchored.
The problem is that the entire mass is often anchored to the slab or the structure at relatively few points. So when the building begins to drift sideways in an earthquake, these rigid blocks of shelving want to resist that movement, which places massive shearing forces on their anchors.
And if the anchors fail,
If they break free, they become multi-story impact hazards. They can literally topple over and shear off columns, impact shear walls, or compromise the entire floor system above and below them.
so the mitigation for this has to go way beyond standard seismic restraint.
Oh, absolutely. It demands three critical layers of mitigation. First, the building itself needs a very tight, controlled drift envelope. The structure simply cannot be allowed to move beyond a specific, very small tolerance.
So you design the whole building around the library shelving.
In a way, yes. Second, you often need drift isolation joints in the slab near the shelving units to decouple the main structure's movement from the localized support for the shelving. And third, you need meticulous specialized lateral restraint calculations just for the shelving unit itself to make sure its inertia is managed without transferring excessive force back into the primary structure. It's a critical systemic failure mode that has to be engineered out from the beginning.
We've moved from theory to practice now, looking at two specific, complex, real-world management scenarios. The key insight here seems to be that performance, and especially occupant comfort, often requires dynamic tuning and surgical intervention, not just brute force stiffness.
That's exactly right. Preventing collapse is the basic mandate. That's code. But ensuring a building functions comfortably and continuously under predictable stress, that is high-level engineering.
So let's look at scenario 4.1. Torsional wind sway in a municipal center. It's a 12-story justice center, structurally sound, but it's failing the occupant comfort test during wind events. It's peaking at 19 milli-G acceleration.
And that 19 milli-G figure is the critical threshold. Above roughly 15 milli-G, which is thousands of a G-force, occupants begin to physically feel the building sway.
What does that feel like?
It can lead to motion sickness, anxiety, a general sense of unease, and it eventually leads to the failure of the building's operational purpose, even if the structure itself is perfectly safe. Nobody wants to work in a building that makes them seasick.
And the root cause here isn't simple wind pressure. It's torsional irregularity. The structure is twisting. The data showed a torsional irregularity index of 1.4. What does that index signify? Why is that number so critical?
A standard symmetrical building has an index of 1.0. A 1.4 index means the building's rigidity is highly asymmetric. The lateral forces from the wind are causing the structure to twist around a point that is significantly offset from its center of mass.
And that twisting motion is what makes people uncomfortable.
It generates far more problematic forces for occupant comfort than simple side-to-side drift. And compounding that was a 22% stiffness mismatch between the building's wings and a resonance frequency that aligned perfectly with the wind forcing when it hit the building at a 17-degree angle off orthogonal.
It was a perfect asymmetric storm.
It was. And the required fix is a master class in this kind of dynamic surgical tuning. The initial expensive impulse might be to just add massive shear walls or thicken the concrete core.
The brute force approach.
The brute force approach. But that's often inefficient, and it can even be counterproductive. Simply stiffening the structure might just shift its natural frequency into an even worse alignment with common wind speeds.
So what was the surgical workflow they used instead?
First, they had to remodel the complex aeroelastic behavior using directional wind tunnel testing. Then the elegant solution was twofold. First, the targeted addition of secondary outriggers at two specific mechanical floors.
And outriggers are like?
They're cantilevered beams designed to gently link the building's core to its perimeter, which helps redistribute stiffness without adding a massive amount of weight.
And the centerpiece of the solution was the tuned mass damper.
Yes, and specifically calibrated for that precise failure mode. A tuned mass damper, or TMD, is essentially a giant, heavy pendulum. It's a heavyweight, often on hydraulic or lubricated sliders, and it's calibrated to oscillate at the exact opposite frequency of the problematic building sway.
So it cancels out the motion?
It cancels out the motion by absorbing the energy. And crucially, this one wasn't just tuned to the building's primary frequency. It was specifically tuned to absorb energy at that 17-degree off-axis forcing vector that was causing the torsional resonance. It was incredibly precise.
That sounds incredibly expensive. Is a custom calibrated TMD actually more cost-effective than just pouring more concrete?
It's more complex, but it's often more efficient in the long term. Increasing the building's mass or stiffness might require major structural demolition, maybe even foundation upgrades. The TMD, while costly upfront, is a mechanical system you install high up in the building that specifically targets the dynamic problem without dramatically increasing the static load or overbuilding the structure. It's an efficiency trade-off, investing in sophisticated damping rather than brute resistance.
And they also had to deal with the consequential failures re-anchoring elevator guide rails, adjusting facade gasket tolerances.
Right, because once the building is moving slightly more than originally intended, even if it's now damped, all of the secondary systems can start to fail. Elevator rails scrape or derail. Facade gaskets can shear, leading to water ingress. The whole system had to be finely tuned to this new, dynamically optimized reality.
Okay, let's move to the second scenario. Thermal drift differential in a massive airport terminal with these long, curved steel trusses. And this is a failure caused by uneven solar exposure.
A failure driven entirely by thermal asymmetry. During peak heat waves, the land side of the terminal, which faces parking lots and dark, heat-absorbing pavement, reached temperatures 19 degrees Celsius higher than the air side, which benefits from open concrete aprons and the continuous airflow from airplane engines.
A 19 degrees Celsius difference across a single long-span steel structure. That has to generate immense unequal expansion forces.
The consequences were immediate and critical. The vertical camber mismatch, that's the difference in the vertical deflection of the curved trusses, hit 14 millimeters.
And that differential expansion caused huge operational failures.
It did. Gate bridge misfit, which means the jet bridges couldn't dock cleanly with the airplanes. And a curtain wall anchor misalignment of 11 millimeters, which was risking the structural integrity of the entire glass envelope.
So thermal asymmetry is not a secondary condition in a building like this. It is a primary governing dynamic load.
It absolutely is.
So how did they solve that expansion problem surgically? You can't just hold it back.
You can't. The forces involved in trying to restrain 14 millimeters of thermal expansion in a steel truss of that scale are comparable to major wind loads. The solution was to stop resisting the movement and start absorbing it gracefully.
Absorb it how?
The workflow involved installing sliding knife plate anchors. So instead of a fixed bolt connection, the knife plate is a connection that allows for controlled, limited vertical movement while still maintaining its shear and load transfer capacity.
And for the curtain wall?
They retrofitted the curtain wall anchors with slotted vertical rails. It's like a track. This allowed the vertical element of the curtain wall to slide within the anchor, absorbing that 11-millimeter displacement without shearing the gasket or cracking the glass.
And critically, they also addressed the source by implementing a comprehensive solar load shading strategy for that hotter landside zone.
Exactly. High-level engineering requires both dynamic management and proactive mitigation. You manage the expansion you can't avoid through sophisticated joints, and you reduce the overall expansion load through architectural shielding.
So the lesson is, in large-span steel systems, you have to design specialized connections that anticipate and accommodate thermal movement as the governing load. You have to abandon fixed joints in any area of thermal asymmetry.
That's the key takeaway.
We've covered foundation stability, policy implementation, dynamic performance tuning. We'll try to synthesize these discrete challenges now into the comprehensive strategic mindset that's required for the next generation of master builders.
I think the highest form of architectural intelligence is exactly that, translation. Translating what seem like insurmountable constraints, whether they're geological or chemical or political, into creative design prompts.
And the digest provides 2 exceptional synthesis prompts that do just that. Let's explore the first one, the atmospheric responsive civic wing.
This is a design challenge that requires you to create a building annex where the structure, the shading, and the airflow actively respond to the daily atmospheric chemistry, not just temperature, but real-time KIORO, smog, and particulate levels. The building's form has to physically adjust its openings and shading patterns to optimize air quality and comfort using the principles we discussed earlier with that carbon-adaptive steel.
And the constraints listed are the true design drivers here. First, it has to maintain passive performance if the sensors fail. And second, it has to be integrated into an existing building that has a mismatched structural grid.
That passive performance constraint is crucial. It forces the designer to rely on inherent material intelligence and geometry. Maybe it's louvers that naturally close below a certain wind speed, regardless of what a sensor tells them. And the integration into a mismatched grid forces the structural solution to prioritize flexibility and independent support systems. The new annex has to be able to move relative to the older structure without causing failure at that interface.
So you need sophisticated structural isolation joints and a complex load path negotiation.
You do.
The second prompt, the geothermal negotiated civic pavilion, is equally complex. It demands an integration with deep earth physics.
It asks for a spatial form that literally emerges from negotiating the geothermal gradients beneath the site. The public room should expand or contract, both spatially and thermally based on real-time subsoil temperature mapping.
So you could walk into a public hall whose layout literally changes based on the cooling potential of the earth right below it.
The design has to be deeply earth-coupled, utilizing thermal mass and subterranean heat exchange. And again, the constraint focus is critical. Maintaining a unified architectural language despite the necessary plan irregularities that arise from following the optimal thermal contours of the ground. And on top of that, it has to operate passively at least 50% of the time.
Which means the building has to use daylighting and earth temperature exchange to meet most of its conditioning needs.
It necessitates a fully integrated strategy of building layout, material selection, and site geology mapping for the very first sketch.
Shifting to life safety, let's just revisit those critical IBC mandates for high-rise fire safety systems. This feels like the ultimate lesson in failure compartmentalization.
It is. High-rise fire safety is completely non-negotiable, and it requires system redundancy at multiple levels. The IBC, the International Building Code, mandates 2 independent water sources, say a city connection plus a massive reserve tank for firefighting.
And more specifically, because of the height, you need pressure zone separation.
Absolutely. Because of the stack height, the internal water pressure in the pipes is extreme. Pressure zone separation is mandatory to prevent reverse flow if there's a pressure drop, say from a pump failure or a fire on an upper floor. If one zone fails, it cannot be allowed to compromise the system's ability to deliver water to the rest of the building.
And mandatory pump redundancy.
Yes. A single pump failure cannot be allowed to compromise the entire fire suppression system. The takeaway is profound. High-rise water systems are designed as pressurized, critical ecosystems where failure has to be intentionally compartmentalized and isolated. Redundancy is not a luxury. It is a fundamental life safety design requirement.
Finally, we see how all these domains, the geology, the policy, the dynamic engineering, life safety, they all converge in real-world RFP opportunities. The digest gives the example of the conceptual Sahelian Borderlands Peace and Infrastructure Hub.
This is the ultimate proving ground for this new model of the master builder strategist. This hub, envisioned for transboundary governance, requires architecture that blends regional planning, policy design, water management, and engineering resilience, all in an incredibly politically sensitive area.
It requires using infrastructure not just to solve a local problem, but to act as a mechanism for international diplomacy, using physical construction and resource management to stabilize a volatile region.
You have to negotiate water rights, design resilient, adaptive structures, and integrate political stability protocols directly into the physical layout of the buildings and the landscape.
It positions the design practice at the highest strategic level possible. Infrastructure diplomacy, where the physical building facilitates policy and stabilizes political boundaries.
It's the ultimate synthesis.
This has been an incredibly intensive analysis, all drawn from the architectural insights with KING-KAMBUF PS ArchitectureDaily Mentorship Digest. We have navigated from stabilizing the frozen ground with cryogenics to understanding how atmospheric chemistry can actually change the ductility of steel.
We've learned why policy has to be designed into utility pipes, and why a stack of library books is a major lateral structural hazard.
The material really forces us to discard this old notion of a static building. Mastery in the AEC world now requires thinking simultaneously as a builder who understands the rigidity of concrete.
A strategist who understands the instability of politics, and an engineer who recognizes the demands of planetary physics. You have to see the structure as just one part of a continuous changing global system.
Because if you fail to design for that thermal asymmetry, or the invisible forces of capillary action, or the underlying legality of your resource supply, your project is fundamentally flawed. It doesn't matter what its initial budget or aesthetic appeal was.
Which leaves us with the profound reflection that was posed in the digest. A crucial question for you, the master builder, to continue to explore and to challenge yourself with. And it's this: how can the world's infrastructure become flexible enough to respond to its climate, but stable enough to govern its future?
Thank you for joining us for this deep dive into advanced architectural insights here on Beyond the Comfort Zone. Until next time, keep refining your craft and thinking beyond the comfort zone.